Hi there, Mr. Sutton here, bringing you the BC Calculus 710 Extra Practice number 7 solutions on alternating series test. For this free response problem, we have a function f with derivatives for all orders between -1 and 1, and we've got some conditions about f of 0 is 0, f prime of 0 is 1, and for all the derivatives of 2 and higher, we have this crazy formula that we're going to have to use quite a bit. So let's see here. We're also told that the Maclaurin series for f converges on absolute value of x less than 1. Great. So our first task here, we want to show that the first 4 non-zero terms of the Maclaurin series for f are as follows. And then write a general term for the Maclaurin series for f. So we already know what the answer is going to be. We just have to show that we get this when we follow our function building pattern that we always use. So in general, we know that a Maclaurin series, you're going to have f of 0 plus f prime of 0 times x plus, and I'm going to keep going here because I need to make it all the way up to x to the 4th. So I'm going to have f double prime of 0 x squared over 2 factorial, f triple prime of 0 x cubed over 3 factorial, plus we have one more again, we're making it to x to the 4th. And they also said the first 4 non-zero terms, and f of 0 is 0, so we got to go one more. Fourth derivative of 0 times x to the 4th over 4 factorial, adding that. All right, so this is what we have to figure out first, is what these are, and then we'll come up with a general term after we've got a little bit more said about these. But in general, our general term should be the nth derivative of 0 times x to the n over n factorial. So we'll get there when we get there. All right, so f of 0, we already know that that's 0. We already know that f prime of 0 is 1. But we need to figure out the second, third, and fourth derivatives of 0 using this formula up here. So for the second derivative of 0, and this formula is a little tricky, if I'm doing the second derivative, that means that n plus 1, that whole expression, really has a value of 2, which means that n by itself in this formula is just 1. If I'm doing the second derivative, I'm using an n value of 1. So that's going to be -1 times the first derivative. So -1 times my first derivative, which they said was 1 up here. So -1 times 1 gives me -1. Now for the third derivative, well, now I'm using an n value of 2, since 2 plus 1 is really 3. So this is going to be -2 times the second derivative, which we just found was -1. So -2 times -1, which is +2. And now I just need one more, the fourth derivative. Well, now I'm using an n value up here of 3. So this is -3 times the third derivative, which we said was 2. So that all comes out to -6. And while we're at it, let's come up with the nth derivative. So this is going to be a little bit trickier. For the general term, for the nth derivative, there is a pattern with these derivatives. They are alternating, which you'll see if you keep going. And maybe we'll just do one more in our heads just to see the pattern a little more clearly. If we were to take the fifth derivative, this would be -4 times the fourth derivative, so -4 times -6, which would give us 24. So let's see here, -1, 2, -6, 24. What's the pattern there? Well, those are all factorials. This is -1 factorial. This is +2 factorial. This is -3 factorial. And the next thing would be a +4 factorial. So for the nth derivative, you have alternating. So you have -1 to the n plus 1. And you're going to have a factorial here. Now, which factorial is it going to be? So when you did the fourth derivative, you got -3rd factorial. So the factorial is always going to be 1 less than the derivative. So this would then be the n minus 1 factorial. And let's just make sure we have the right thing for this n plus 1 here. So if I did let's say that I did the fourth derivative, that would be -1 to the 4 plus 1, which would come out negative, which this one does. All right, so we're good. So this is our general derivative. Putting everything together now, back into my Maclaurin formula here, I have f of 0, which was 0, f prime of 0 we said was 1, so this is 1x, which is the first term, so we're off to a good start. After that, f double prime of 0 we said was negative 1, so this is negative x squared over 2 factorial. After that, we have, let's see, triple prime is 2, so this is plus 2x cubed over 3 factorial. Next one, we have minus 6 x to the 4th over 4 factorial. And then finally, we have, let's see here, negative 1 to the n plus 1, n minus 1 factorial, all of that times x to the n over n factorial. We're not quite done yet, though, because they wanted us to show that the first 4 non-zero terms were this right here, and this is a little bit different. So let's go back and simplify a bit, just to make sure our answer actually matches theirs. So we have an x, we have a minus x squared over 2, I can write that as. And now for this next one, we have, let's see here, 2 over 6, which is going to reduce to 1 over 3, so this is x cubed over 3. On this next one, we have 6 over 24, which reduces to 1 over 4, so x to the 4th over 4 being subtracted. And there is a little bit of a pattern here. I mean, you could definitely write the general term just by looking at these. In fact, you could have written the general term just by looking at what they gave us in the beginning. But taking a look at what we actually wrote for the general term by constructing this from scratch, we have the alternating. We have an n plus 1 factorial and an n factorial. Now, n factorial is really just n times n minus 1 factorial. So those n minus 1 factorials can cancel, just leaving me with an n in the denominator. So I have negative 1 to the n plus 1 times x to the n over n for my general term. And I have finally shown what I set out to show at the beginning of this problem. For this problem part, they want us to determine whether the Maclaurin series in part A converges absolutely, conditionally, or diverges at x equals 1. So just to recall from part A, this was right here, this very last piece, this was our general term. So I'm going to start by writing that in sigma form. Summation from 1 to infinity of negative 1 to the n plus 1 times x to the n over n. This is the series from part A. So we want to figure out what happens if I plug in 1 for x. So f of 1 is just going to be, well, 1 to the n is just 1. So we really just end up with negative 1 to the n plus 1 all over n. And I want to know if this series now converges absolutely, conditionally, or diverges. We first consider the absolute value version of this, which basically means we have a positive 1 over n. This is the harmonic series, which we know diverges. So this series does not converge absolutely. Now the original series right here, this by itself is the alternating harmonic series. So the original is going to converge conditionally because it is the alternating harmonic series. It converges with alternating thrown in. On this part, we want to write the first 4 non-zero terms in general term of a Maclaurin series for g, which is essentially the integral from 0 to x of f of t dt. So from part A, again, here was the f of x function, or at least the series for it. So now I basically want to take the antiderivative of this and plug in 0 and x. If I do that, so I would basically get the antiderivative of all this stuff with t's in it instead of x's. I would then plug in x and 0. Now the key here, before I subtract those and write all of that out, is all these things, when you take the antiderivative of them, you're going to get a variable. So, for example, this first one, if you write this as the antiderivative of x with a t thrown in, this would be t squared over 2. And the rest of these are going to have t's in them, which means if you plug in 0, all of that's going to get zeroed out. So really, all that's going to be left over when you go through that whole process is whatever you would have gotten when you took the antiderivative and plugged x in. All of which is to say, I'm not going to write all of that out. I'm just going to take the antiderivative of all of this stuff with x, and I'm not going to need a plus c at the end because I really am taking a definite integral. It's just all the stuff with 0, it just gets zeroed out. So antiderivative of x using my reverse power rule, this is going to be x squared over 2. And then for this next term, so this is all g of x now. For this next term, this bumps up to a 3. Dividing by that, we have x cubed over 6, and we're subtracting that. Next exponent's going to bump up to a 4. Dividing by that, we have x to the 4th over 12 that we're adding. And now we're going to have, let's see here, this is going to be x to the 5th over 20 that we're subtracting. And more generally, we're going to have negative 1 to the n plus 1, x to the n plus 1, all over n plus 1 times n. And that's all they asked for. For the last part of this problem, they're saying that p sub n of 1/2 represents the nth degree Taylor polynomial for g about x equals 0, evaluated at x equals 1/2. So basically, this is an nth degree approximation of x equals 1/2 plugged into p. And g is this function from part C that we already defined. Here's the g function again, just so we can use it on this problem. They want us to use the alternating series error bound to show that p sub 4 of 1/2 minus g of 1/2 is less than 500 in terms of absolute value. Basically, they're asking us for the error bound if we use a fourth, because it's p sub 4, a fourth degree Taylor approximation at x equals 1/2. Okay, so we don't actually need to show them what the approximation is. We just need to show that the error is less than this 1 over 500. Well, since these terms are alternating, and if you're plugging in 1/2 for x, so a number between 0 and 1, these terms are absolutely definitely going to be decreasing in absolute value to 0. Since we have all of that going on, we know that the error is going to be less than the absolute value of the next term. This is the alternating series error bound that they were just telling us to use. So once we've shown that, all we have to do is actually just find the absolute value of the next term and show that that's less than 1 over 500. Well, what is the next term? If you're using a fourth degree Taylor approximation here, that means your next term is going to be the fifth degree term, this x to the 5th over 20. So we just need to plug 1/2 into the x to the 5th over 20, and we just need the absolute value, so we don't need this negative in here. So I'm just going to write 1/2 to the 5th over 20, or you could write it as 1 over 2 to the 5th times 20. Whether you want to deal with that fraction sooner or later is up to you. But at some point, you do end up with a 2 to the 5th in your denominator. So what does this come out to? Well, 2 to the 5th is 32. 2 times 32 is going to be 64, plus another 0 in there. We have 1 over 640. 640 is a larger denominator than 500. That means that this fraction is smaller than 1 over 500, which proves what they were telling us to prove up here. For this free response problem, we have the Maclaurin series for ln of 1 over 1 minus x given as x to the n over n, and they also gave us the interval of convergence for that. First task on this is to find the Maclaurin series for ln of 1 over 1 plus 3x and determine the IOC. Okay, well, we're basically just doing Maclaurin transformation. So all that we did here was we substituted negative 3x for x in the original. So to get the Maclaurin series, we're just going to do that substitution in the series itself. So I'm going to write negative 3x to the n over n. And this isn't quite a Maclaurin series yet. You're not supposed to have things like this inside of a parentheses with an exponent outside. So I'm just going to kind of distribute that negative. I'm going to write this as negative 1 to the n times 3 to the n times x to the n. You could also write this as just negative 3 to the n times x to the n. The key is that x has to be kind of on its own here. Now for the interval of convergence, we're going to do pretty much the same idea and substitute negative 3x for x up here. So I've got negative 1 less than or equal to negative 3x less than 1. And now dividing everything by negative 3 to isolate x, I have a positive 1/3 over here and a negative 1/3 here. And don't forget, when you divide by a negative, all your inequalities switch. So now just rewriting this in a more logical order, I can write negative 1/3 is less than x is less than or equal to positive 1/3. For this part of the problem, they want us to find the value of the summation of negative 1 to the n over n. Now, the key on this one, since you might be wondering, how do I find a sum if it's not a geometric series? Well, take a look back at the original part of the problem here. So this is the summation of x to the n over n, and this is pretty much the same thing, only we have a value of negative 1 instead of x. So basically, this right here is just this function with negative 1 plugged in. Now, the million-dollar question is, can I actually just plug negative 1 into ln of 1 over 1 minus x and be done with it? And the answer is yes. We know that the interval of convergence for this series to the original function is negative 1 less than or equal to x less than 1. This is basically saying that for all x values from negative 1 to a little bit less than positive 1, this series, whatever you plug into x here and whatever you plug into x here, you're going to get the same value back. These two things are the same on this interval. So since this series converges at x equals negative 1, to figure out what this series is, we can just plug negative 1 into this function. So we have ln of 1 over 1 minus negative 1. So this is going to be 1 over 2 inside the ln, so ln of 1/2. And there's really no reason to go any further than that. For this part, we want a value of p such that negative 1 to the n over n to the p converges, but 1 over n to the 2p does not. All right, well, looking at this first series, this series is going to converge if p is greater than 0. If p is greater than 0, then the terms of this series, they're going to alternate regardless, but they will also decrease in absolute value to 0, because p greater than 0 means that your denominator is actually going to be growing. So this means that for values of p greater than 0, this will converge by the alternating series test. So we want a p-value that's bigger than 0, positive. Okay, now let's look at this other series. So for this one, by the p-series test, this is going to diverge if this exponent on n, this 2p, is less than or equal to 1. Which is to say, this will diverge if p is less than or equal to 1/2. So we essentially want to pick a p-value that is between 0 and 1/2, including 1/2. Well, there's a lot of different values you could pick. I picked 1/4. You could have picked 1/8, or you could have even picked 1/2. So anything from 0 to 1/2, and you would be good, but not including 0. For this last part of the problem, which is kind of like part C, they want a p-value such that 1 over n to the p diverges and 1 over n to the 2p converges. Well, by the p-series test, taking a look at both of these, 1 over n to the p diverges if p is less than or equal to 1. So we need a p-value that's less than or equal to 1 to make this first series diverge. At the same time, by the p-series test, 1 over n to the 2p is going to converge if this 2p exponent is greater than 1. So to converge, we need p to be greater than 1/2. So this means we need a p-value such that 1/2 is less than p is less than or equal to 1. Basically between 1/2 and 1, including 1. So any number in between here will do, and I'm just going to pick a number in there like 3/4 and call it done.